Welcome back to Chem 4300. In this video, we're going to finish up Chapter 12 and look briefly at the results of what you would get if you looked at this particular type of situation where a quantum particle, free particle, is approaching a barrier of a finite thickness. Now this particular problem, which we're going to model like this with a very sort of simple function for the potential energy, which is just simply a square barrier where it has some value of 0 up to x equals 0, and then from x equals a out at 0, and then between x equals 0 and x equals a, we have some constant value of v naught. And this type of problem is very important in chemistry and electronics and all types of applications, many types of applications. For example, this is the type of barrier that you might use if you want to understand the rates of electron or proton transfers in chemical reactions, or if you want to understand how ammonia molecules will invert in their structure. For example, the emission of alpha particles in radioactive nuclei, or if you're looking at transistors and electronics, a lot of the types of devices will make use of this type of tunneling behavior that we see through this type of barrier. And then the last thing mentioned is that I'll give you an example at the end here of how you can use this type of behavior to image the surface of materials with this kind of tunneling current that would flow between a tip and some kind of metallic surface. So let's take a look at this problem in a little bit more detail, but again, I'm going to leave most of the derivations for you to do at home. I'm just going to give you the final results here. So just to kind of review what we knew from last time, we know that when the potential energy is equal to 0 on the left and on the right of the barrier, then we're going to have oscillatory solutions, and the energy is the same on both sides, so they have the same wave number k. But it's inside the barrier here where we're going to consider two possible cases when the total energy of the particle is not bigger than V naught, so where the classical particle would not be able to penetrate this barrier. And then when the energy is greater than V naught, where the classical particle would be able to go past this barrier. And what we're going to look at in terms of the quantum behavior is whether the quantum behavior, the quantum particle can actually penetrate even this behavior, and the quantum particle will actually be reflected when we have this condition over here. So we're going to take the two wave functions for these two cases inside the barrier as going to be what we call wave function 2 and wave function 3 inside the barrier. This will be the case when the energy is less than the potential, and in that case, the wave function are going to be exponential decays, although written right here with growth and decays, but we'll soon see that that G term is going to have to be, is non-physical, won't be set to 0. And then when the energy is greater than the potential energy of the barrier, then we have an oscillatory solution inside the barrier. So in this case, it will be oscillatory on both sides and inside. And in this case, it'll be oscillatory here on the left and right, but a decay inside. So that's the picture that we expect to have. So we know that we have a particle that's coming from the left, and when it hits the barrier, if it has enough potential energy to exceed, it won't be reflected back. So when we look at the right side of the wave function, we have this term here, which represents a wave function going from right to left. And we're going to assume that if it makes it to the other side, this term is not going to come back. So that term is going to be 0. So we're going to set d equal to 0 to account for that sort of understanding of the problem. So the next thing we're going to do is we're going to take our constraint that the wave function has to be finite, single valued, and continuous. So when the wave function meets here, on this side and on this side, it should be a single value, and it should vary continuously, and the same over here. So that's these two constraints. So when we plug those in, those two wave functions on the previous page, these guys and over here, then we will get results depending upon whether we're in case 1 or case 2. So we'll work through these in homework. I'm just going to give you the results. So let's look at the results from this case here, where we don't have enough energy to surmount the barrier. And in that case, inside the barrier, our wave function is just going to be a decay. I got rid of the growth term because that's not physical. And if I took the wave functions on all sides, the left, the right, and inside, then we have an oscillatory solution on the left. We have a decay inside the barrier. And if the decay does not make it to zero by the time it reaches the end of the barrier, then there'll be a finite probability that the particle will exist on the other side of the barrier where it will have an oscillatory solution. So this is what the probability would look like through the left in the barrier and on the right side of the barrier. And this is, again, that's a pretty remarkable result, something that you would not expect for a classical particle. A classical particle flying along this direction would hit this potential energy and barrier, and it would bounce right back because it doesn't have enough energy to surmount the barrier. But the quantum particle will tunnel through, and if it doesn't die by the time it gets to the other side, then it has a finite probability of escaping to the other side and continuing on with its free particle behavior. So this is a really sort of surprising result. Again, not surprising given what we learned in the last video, but you can imagine that this is going to be relevant for a lot of physical applications. Now we can also calculate the transmission coefficient through the barrier by looking at the ratio of those probabilities with their probability fluxes there. And I'm not going to go through the derivation, but you get an expression like this where you have this hyperbolic sine function. So what I'm going to do is show you a limiting case. If you have a small argument for this hyperbolic sine, you can approximate it to be this term here. And what I'm going to do is then take the transmission and use this approximation to give me an expression like that. And of course the reflectance is going to be obtained from t plus r equals 1, so I can just take 1 minus the transmission to get the reflection from that same equation here. So hold this thought. We're going to come back to this when we bring it all together once we look at the other case. But what's important to understand is that this transmission through the barrier, when we don't have enough energy classically to get through it, is what we sort of expect. We know that as the barrier gets thicker and thicker, so A goes to infinity, then you can see that as A goes to infinity, this decay goes to 0, and our reflectance comes back to 1, and our transmission goes to 0. That's as expected. As the potential energy goes to infinity, then this whole term over here is going to go to 0, and we're going to have perfect reflection and no transmission. Again, that's what we expect as the barrier gets higher and higher. And as the mass goes to infinity, you see that this wave number here term is also going to get bigger and bigger, which has the same effect as the thickness increasing. And so that's going to cause a decay, which kills this term here and gets us back to reflectance of 1 and a transmission of 0 in this limiting behavior. Now let's look at the other case when we approach the barrier and we have an energy that exceeds the barrier height. And in this case, we're going to have an oscillatory behavior inside the barrier. And so the classical particle would always go past this. But now for the quantum particle, we have to include the possibility that it will actually encounter this barrier and be reflected, even though it has enough total energy to get past the barrier. So again, I'm going to leave this as a homework assignment. You're going to calculate the transmission coefficient in this case where we have more than enough energy to cross the barrier. And you see you get an expression that looks kind of similar to the last expression, but this is now a sine, not a hyperbolic sine here. So that's not a typo. It changes to an oscillatory type of behavior like this. And so what you get and then is that you can combine this with the previous section for the behavior when it doesn't have enough energy, when the ratio of the total energy to the potential energy barrier is less than 1, and then to the region where it exceeds the energy of the potential barrier, which is from 1 out, and you see how the transmission and the reflection behave. So you can see that when you don't have enough energy, this is the transmission here, there is no transmission as expected, but as you increase in your total energy, even if you're below the threshold of the potential energy barrier, you already start seeing transmission through. The electron is tunneling through this barrier as you get to total energies that are still less than the barrier. And then you can see that when you reach 1, when you reach the energy of the barrier, then you are already here at about something like 30-some% transmission. And then as you continue increasing the energy, eventually you get this sort of oscillatory behavior, and then you reach the limit of the classical particle where you have 100% transmission when you exceed the threshold, the total energy of the barrier. And of course, the mirror of that is the reflection, that you have complete reflection when the energy is 0. But as the energy increases, you can see the reflection drops, and eventually when you hit 1, then you drop down to about only about 70% reflection, and then you continue on like this, where you have no reflection when you have a very high energy. That again is the classical limit. But this region right here is something that only something that the quantum particle will do. The classical particle would have just been 1 and then dropped for the reflection, and it would have been 0 until it got to 1, and then it would have increased to 1 for the transmission. So one particular application that is very exciting these days is to do something called scanning tunneling microscopy. And this is where you take a surface, a metallic surface, and you place a very sharpened tip, a tip that's sharpened to just like down to an atom, and you can adjust the potential between the surface and the tip so that you can adjust the height of the potential energy height for this barrier of whatever thickness here. So this would be our thickness A there. And as you move across the surface, well, you know that the atoms have the shape, and as you go up and down, when you get to the space between the atoms, then the thickness of the barrier will increase, and when you get closer to the atoms, the thickness will be smaller. And so the current that flows, the tunneling current that flows, will be proportional to the distance between the tip and the surface. And in this way, you can get an image of the surface. And this is an STM image of silicon carbide, and silicon carbide has a hexagonal lattice, and you can see that the image that you get reflects the symmetry of that lattice. You have this hexagonal lattice here, and you can see the regions here where it's dark are the regions where the current drops, and this is where the tip is closer to the surface, to the barriers become smaller, and we have high current here. So this is a really cool application, but there's so many applications of tunneling, and I leave you with a few cool videos to read, for example, how transistors work. But this is a short chapter, but I think it really tells you a lot about how quantum behavior can be exploited in a lot of real-world applications.